Hi, my name is Caroline Turner. I'm a third-year undergraduate at Colorado School of Mines studying mechanical engineering. And I'm here today to talk about the research that I've been doing with Dr. Yu, Ben Schneiderman, and Tushar Telemasre over the past 8 months. So our topic is interdiffusion barrier for multi-material structures. So you might ask, what's the driving purpose behind our research? Well, currently there's no solution to joining dissimilar materials due to thermal, physical, and chemical incompatibilities. So this restricts advances in engineering significantly as it pertains to metalworking in aerospace, automotive, and other similar applications. So, in order to continue the progression of engineering challenges that our ever-changing world presents, this problem must be addressed. So we have two primary objectives. The first one is to understand how the composition of multi-principal element alloys affects the diffusion and deformation mechanisms. And the second one is to design MPEAs that can act as a diffusion barrier to enable joining of incompatible materials while maintaining a physical interlayer which reflects the desired physical outcome required of its application. So here are our methods. First, we have a basic game plan of how we wanted to attack our research. So task one, we wanted to make sure that we had a pretty strong understanding of some great alloys that we could actually work with. So first, we pared down all of our options with computational composition design, which we'll get into later. And then from there, we did some sample fabrication of our top ranked alloys, like which ones performed well in our computational composition design. And then we moved on from there. The third task is to test diffusion behavior. Task 4 is to test phase stability. And task 5 was to understand the mechanical properties that these new MPEAs would present and really test them and make sure that they were giving us the physical outcomes we desired. So first, our computational MPEA composition design was a 3-step process employed to determine filler alloys for specific applications, which we have at the bottom of the screen. So first, there was a filtration code that was written in MATLAB to rank MPEA systems depending on the compatibility. This compatibility was between thermal, chemical, and physical compatibility. The second step was high throughput simulations for the top ranked MPEA systems were run using the Scheele solidification module and thermocalc via TC Python. The third and final step was phase diagrams calculated by thermocalc CalFAD software were used to investigate filler substrate interactions. So this methodology was used for the 3 applications described below. So first, here's a basic understanding of what our filtration code consisted of. So you can see on the left-hand side of the screen, it's just kind of a diagram explaining like the physical dimensioning of our alloys that we were trying to figure out. And the highest ranked for this specific nickel-based alloy that we were looking for was, and you can see it on the screen below. And then to the right, you can see the order of filtration. So first it went through an atomic size mismatch, then a VEC or valence electron concentration criteria, then a configurational entropy criteria, and finally enthalpy of mixing. So we needed to make sure that these 4 criteria were met in order for us to feel confident about our microstructures of our MPEAs. So here are some basic Scheele solidification results we got from the same nickel-based alloy, which you can pause and watch if you want to. And then here's some examples of our brazing for our nickel-based super alloy, our sample fabrication. So here's our composition that we came up with. And it was fabricated via arc melting of the constituent elements, which were at least 99% pure prior to fabrication. And these buttons were we really wanted to make sure that they were homogeneous. So they were remelted 3 times to make sure that it had bulk homogeneity before we moved on to further testing. So next we did some compositional analysis. Bulk compositional analysis was done for each arc melted button via an X-ray fluorescence using the SciAmps X200 handheld XRF analyzer. So whole or nearly whole buttons were used, and the flattest face of each button was ground using 240 grit abrasive paper until all of the oxide was removed so that we could get a clean scan. And then the XRF device was used on that clean surface. So what work are we currently working on? So present work as of January 2021, we're currently working with an alloy, which I'm not allowed to discuss because it's unpublished, but we're having some success with this alloy. But we have a processing route for how we want to mechanically test it. So first we're trying to arc melt the button, and then we're going to stress relieve it at 80 degrees Celsius for an hour. And then we're going to use the 240 grit paper to do some oxide removal, then cold roll it, and then use a water jet cut and anneal at 850 degrees Celsius for 2 hours, and then do some fine grinding, and then finally we'll do a tensile test, which you can see on the right-hand side of the screen. That's an example of what we're going to be doing. So some of the challenges that are currently being presented, one, direct furnace brazing results in eutectic melting, which is not what we're looking for. Eutectic melting is homogeneous mixture of substrates that solidifies at a single temperature that's less than the melting point of any of its constituents. So what we're going to try to do in upcoming months is to try sequential joining approach in the vacuum furnace. And here are some of the results we've yielded with the direct furnace brazing prior to our sequential joining assembly. And then the second challenge we're seeing right now is that we have a single substrate wettability test showing an inability to melt on a steel substrate at 1175 degrees Celsius. So we're looking to increase the temperature and see how that pans out for us. So our current research tasks as of spring 2021, I've learned how to use the Vickers hardness testing machine to test material properties, specifically hardness. The second thing I've learned is how to prepare material to be arc melted. The third thing I've learned how to do is to operate a vacuum furnace. And I've become pretty well versed in how to sample prep for metallographic testing. So I've learned how to grind and polish samples using an auto polisher. The primary source of funding for this project is the National Science Foundation. And here are some of my sources. I hope you guys have a great day. Thanks for joining me.